episode number 19 of the Piezo SHOCK Show, where I answer your questions every day on ultrasonic transducers and piezoelectric devices. So today I'm going to be going over the question, how do you measure the operating power of an ultrasonic transducer? So let's go ahead and define what power is. And when I talk about power, I mean real power. I mean dissipated energy, either that's dissipated to the piezo itself in terms of heating due to the mechanical movement, or actually imparted to the external environment. And we'll go over that idea again. But essentially, it's applying that idea of force, energy equals work times distance, but except we apply that in electrical terms, and not upside down but this way. So we find basically the average power dissipated between a voltage and a current flow. And by analyzing that, and basically this is the equation to take the DC average of power dissipated. This is not power within a cycle. If you had this achieved this if you had tuned this up to a cycle, you would actually be able to find the energy dissipated, because part of the time you're putting in energy and you're taking out, but the balance left, or the negative balance of energy, you could say, or the rate of development of that negative balance of energy that you're not able to draw back from your piezoelectric device, that is the true power dissipated. So, for example, if you drive a capacitor with 100 volts, for example, piezo at off resonance, 1 kilohertz, there's going to be very low power dissipated, because you're charging up the capacitor and you're charging it down. But that charging up and charging down phenomenon is not dissipating energy in the material. Yes, perhaps your driver itself is being inefficient in the way it's taking out energy back from your capacitor. But energy is not being dissipated in the capacitor. It's not doing external work that can't be recovered. Effectively, for example, if you charge up a capacitor, you could dissipate that over a resistor. And that would sort of sum up the energy stored on the capacitor. So we're talking about real power, and real power, which is the actual dissipated energy in the environment. So I just want to get really practical here and describe how do you measure this on an oscilloscope. And you can do this either if you're using a ground side resistor to measure power, or if you are using a current probe. So in blue we have voltage, and in red we have current, and they're symmetrical about the about their axes. So they're the maximum voltage is approximately the same as the negative voltage, and there's no real DC component. Even if there was a DC component in voltage, for the calculations that I'm talking about, it wouldn't actually matter as long as you can get the thing in the screen. So let's continue. So we have voltage and current, and if you utilize a math channel in your oscilloscope, you will then get if you multiply those two together, you'll then get a waveform that's the instantaneous power delivered and extracted from your transducer. And obviously, if you extract the same amount as you take back, that is, if the area of that power curve is the same, the multiplication of voltage and current ends up being 0 at the end on average, and that means you're not extracting, or you're not losing any power. However, for practical devices, that never happens. What we have is that waveform that's generated by multiplying voltage and current. And again, current you can either get from a ground side resistor or from a current probe. If you're using a ground side resistor, you have to account for the energy dissipated in that resistor. That's like whatever power you get, you subtract that by the power dissipated in the resistor itself. So you have to add a subtraction term if that is actually significant. But many times that's just like 1 ohm, or it's small in consideration of your load of your transducer, so you don't have to worry about that power loss. You can directly change your oscilloscope settings. So instead of using so for example, for a 1 ohm resistor, you now have a 1 amp, 1 to 1 amp voltage to amp measurement probe now, or quite simply, you just use a You just use a current probe, and many oscilloscopes do recognize that. But even if they don't recognize that, you can still understand the units that are being read by the oscilloscope, and therefore they should be the same units being put out. So if you have volts being read on your voltage, and if you have amps being read on your amps, as long as they're the same magnitude, you multiply those together. Therefore, you get watts. All right. So when you get this green curve, which is the one that is representative of power, and you take the DC average, so you use the DC average of that. That is the average power dissipated. It's basically going to be offset positive, representing a positive power into your system. If this somehow is negative, that means on average you are extracting power from your transducer. Your transducer does not do that. It consumes power. It doesn't create power. Again, that DC average just does this equation in a little bit more of a simple format by just multiplying those waveforms together and then taking this average by integrating over not necessarily a cycle. You should do this over several cycles, especially on an oscilloscope where you won't get exact cycle numbers on your oscilloscope screen. But you do this over 10, 20 cycles, and you'll have a fairly accurate value for power in terms of milliwatts. So here's a couple of more important things. So again, you take the DC average of the voltage times the current waveforms, that gives you power. From this, you can also calculate the apparent phase angle, because we know that voltage and current, they give rise to an impedance, and that impedance value also has a phase angle. So if you take the tangent of that phase angle, and that's going to equal the power dissipated, that real power, divided by the voltage RMS multiplied by the current RMS. So that's going to give you your phase angle that you can that you'll have for impedance measurements. Finally, the units are in watts, and also, it's important to understand that you are inputting power into your device. That's real power dissipated, and power which is dissipated, basically that offset from the voltage times the current. So you're inputting power in a certain number of watts, and that power is either sent out into the world to do whatever that ultrasonic device was meant to do. Meant to send acoustic waves through a fluid. It's meant to weld. It's meant to do ultrasonic cutting. It's meant to do atomization. It's going to do what it's going to do. That's where some of the power goes. The rest of the power actually is dissipated within the piezo ceramic, and what that ends up happening and doing to your piezo is heating it up. So we typically want to reduce the amount of power dissipated in your piezo, increase the amount that is injected into the environment that's doing the work. There could be many ways of determining this ratio between, and that's one way of looking at efficiency of your piezo. So there's several ways of looking at efficiency, how amplitudes and currents and voltages all propagate through energy space into power space. So you may be familiar with the electromechanical coupling coefficient, which is essentially the electrically stored energy versus the mechanically stored energy for a resonator that involves and that describes a cycle. Through a cycle of excitation, how much energy is being put electrically versus mechanically into the system. There's also efficiency. So what is the power that it takes to drive your final function? Now, your final function, you may not be able to measure that in terms of watts, so you don't get an efficiency. So if you talk about watts in versus watts out, therefore you can talk about an efficiency, but how much is dissipated in the piezo versus how much is injected into the environment. And from a measurement perspective, like if you have your voltage and current probe, you're not going to be able to tell the difference between the voltage that gets dissipated in the piezo versus the voltage that gets that power that gets thrown out into the environment. However, you can do things like look at output parameters. For example, for atomizers, you look at atomization rate. For welders, you may look at you may look at bond strength versus that power, although it's a little more dubious and elusive in some applications, but you usually do have something telling you how well the performance had gone. Another interesting way to understand performance is also to analyze the heat generation. That can also tell you and give you an indication about how much energy is dissipated in your ceramics in your transducer by the heat that's generated within it. So it's another way to understand your efficiency of your device, how much is going in, if you have your, let's say, If you had an atomizer is a little bit more difficult for thermal analysis, but let's say an ultrasonic surgical tool or some type of ultrasonic cutting tool, you had it loaded on top of something, you had it pushed down, and you measured, the rate of heating, let's say, and you measured the power into the piezo, and you also measured the rate of heating when the piezo is by itself. So how many watts does it take for the piezo to heat up when it's oscillating individually? So you can kind of isolate some components and dig into this topic a little bit deeper. Of efficiency, but it's quite important to understand power measurement. It's the real thing, like real power. It's really how much mechanical excitation is occurring, because namely in piezo ceramics we consider that mechanical excitation is the major source of losses. Even for a measurement of 1 kilohertz capacitance for a transducer, we say that the losses occurring in the piezo material mostly are due to the mechanical movement of the device, and those are essentially more lossy than pure polarization due to pure dielectric phenomenon. My name is Hussein Shakani. You are watching the Piezo SHOCK Show. Please leave your questions and comments down below, and follow the description. Follow the links in the description to learn more about my consulting offerings. I produce this show every day, so please give your questions. It'll give me some fodder for some future video ideas. So I look forward to seeing you tomorrow.